Hi, I'm Dalton, and this is Physics 2212, Lab 3, dealing with magnetic fields of a bar magnet. So for the introduction, the overall purpose of this lab is to analyze the field of a bar magnet at different distances from it. Then we'll compare the experimental magnetic fields and look at that with a computer-generated result. And then we'll just talk a little bit about the magnet's distance dependencies for the field and the strength of it. So the basic physics concepts, the mu over 4 pi, that's just constant. And then these equations listed here are some of the stuff dealing with magnetic fields that we'll be using for the calculations. So a little preview of the results. I found my mu value to be 1.455 and got an n value of negative 2.7876. So for the experimental setup here, these are just two images kind of showing what happens. The gray bar is, of course, the magnet, and then the phone with the magnetometer to measure the magnetic field. So we'll do some in-axis, as you can see on the left, and then some perpendicular, as we can see on the right image. So for this, our system will just be the magnet, and the surroundings is going to be everything else. So on-axis field data, this is what I use in the Excel spreadsheet, just some of the data for that. You can take a look if you want. And then here's the graph. This linearized the data that we got from that, and we came up with the line y equals negative 2.7876x minus 15.05. So then for the calculation where I ended up finding the mu value, I used the equation that the magnitude of the magnetic field of the bar magnet is kr to the n. And we also found that that can equal out to an equation where we can solve for mu. So, and this just runs us through the calculations of doing that. Nothing too crazy there. So here's the code. First, here on the left, we can see a function to find the dipole for B. Then we just have some things scaling B, setting our distances, getting all our vectors, things like that. Then on the right, this is just generating all the vectors to be drawn in the GlowScript model, if you want to take a look. So then here we are finding a vector observation at an angle away from the magnet, so in between having some on-axis and perpendicular components instead of just one or the other. And then we end up also graphing that arrow as seen below. So there's a quick look at the computational model. You can see the vectors that generates and just what the magnetic field lines are kind of looking like. And then for the observations, there were several listed, and these are the two that I found to hold true. One being when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And that's fair because when we get further away from the magnet, we do expect the field to get weaker and weaker. And then additionally, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And if we find one to be true, that just makes sense because if you go further away, it gets weaker. It only makes sense that when you come back closer, it gets stronger. So nothing crazy there. Some possible error that could have come from this lab, I think, is maybe the phone magnetometer may have not been super accurate. I don't know the degree to which a phone app can measure that in terms of precision. And additionally, other measurements, such as my measurement of the distances, could have been a little bit wrong. There's a chance that it could have been more precise. So that brings us to the what-if questions for this lab. The first is, what if you hadn't oriented your experiment to compensate for the magnetic north and had instead laid out the meter stick to some angle with respect to Earth's magnetic field and how that would affect the results? Due to the fact that the Earth's magnetic field would now be interacting differently with the systems that we set up, this would cause the values to be different because, of course, Earth's magnetic field will have some impact on the magnetic field of the bar magnet, and those will clash with each other or add to each other in some way if we didn't set it up where it didn't have as much of an effect. And then the other what-if question is, what if you were to stick two identical magnets together end to end and redo the experiment? What would we expect to happen? Well, really, we wouldn't expect all too much other than the results to be multiplied by a scalar constant. And that's because when you take two magnets and put them together, you're not really dealing with two separate magnets anymore. It's essentially creating one magnet with just a stronger field that it exerts. So that field's going to go in the exact same direction. So we're really just changing magnitudes. So it would remain pretty much the same. But that wraps it up. Thank you for listening in.